Welcome to lecture 13. Today we will talk about electric power in AC circuits. Let's talk about the difference between active, reactive and apparent power. And we start with active power. Therefore, let's have a look at an AC circuit. We have an AC current source here. That means a source that delivers a sinusoidal current, and we have a load resistor there, and it is a 10 ohm resistor. And now let's measure the current. And in this lecture we will only deal with ideal elements. I just want to indicate where we measure the values. So, and here we have a current of 1 ampere. And we measure an AC circuit here. That means this 1 ampere is the RMS value of the current. And let's measure the voltage, and the voltage drop here is 10 volts. Yeah, it's no surprise because we have a resistor of 10 ohm and a current of 1 ampere. Therefore, the RMS value of the voltage will be 10 volts. And now we connect a third device, and this is a watt meter. It measures the power. And yeah, you know, electric power is voltage times current, so we measure 10 watts here. Not a surprise. Let's have a look what happens in time domain. So I said we had a current of 1 ampere, and in time domain that means that we have a sinusoidal current with the amplitude square root of 2 times 1 ampere. And the amplitude of our voltage is square root of 2 times 10 volts. And you see we have a resistor here, and therefore voltage and current are in phase. Okay, and now we want to calculate the electric power in every moment. So for every time moment we just multiply voltage and current, and the result looks like this. You know these pictures from the RMS value lecture. Okay, and you see the mean value of the electric power here is the 10 watts we had before in our simulation. So this means in a resistive load we have only positive power, and that means that our energy flow goes always from the source to the resistor. Okay, and now let's have a look at reactive power. We will see in a minute what that is. So let's have the nearly same circuit, but this time we have an inductor in here. And the impedance of our inductor is also 10 ohm. So, and if we measure the current here, we measure 1 ampere. And if we measure the voltage here, we measure 10 volts. And now we connect our watt meter again, and it shows the value of 0. Why does the watt meter shows 0? We have a voltage of 10 volts, we have a current of 1 ampere, and the power is 0? Let's have a look what's happening in time domain. So again, we had our current, the RMS value was 1 ampere, and therefore the amplitude is square root of 2 times 1 ampere. And we have our voltage, and again the voltage was 10 volts, and the amplitude of that is square root of 2 times 10 volts. And here we have this 90-degree phase shift between voltage and current. And now we multiply again voltage and current for every single moment. Okay, so this is the electric power in dependency of the time, and the mean value is 0, as our wattmeter told us. And have a look. There is a time where we have a positive power, so our inductor consumes electric energy, but then there is a period of time where the electric power is negative, and that means that our inductor gives energy back to our network. And the energy the inductor consumes will be stored in a magnetic field, and this field gives its energy back into our electric circuit. But the net power transfer is 0. And that means if you have an inductor, if you had an ideal inductor, and you connect it to your socket and to your power network at home, then your energy counter will not run faster. You don't have to pay for reactive power. Let's have a look what happens if we have a capacitor in our network. So again, we have a current of 1 ampere. The impedance of this capacitor is also 10 ohm. And this leads to a voltage drop of 10 volts. And if we connect our wattmeter again, it shows, you guess it, 0. Let's have a look into time domain. So we have again our current, and we have our voltage drop, and this time we have a phase shift of 90 degrees again, but this time the current is leading. And if we multiply voltage and current in every moment, it leads to this. And you already see it, the mean value of the electric power is 0 again. And that means, as before at the inductor, the capacitor stores energy in an electric field, and then this electric field gives its energy back to the electric network, and so on and so on. And that means that we don't have to pay for it if we connect a capacitor to our power net. But if you just measure the absolute value of the voltage and the absolute value of the current, then the product is not 0. And if we don't have to pay for it, we call this power reactive power. And now there's a third new word, and this is the apparent power. Let's have a network again, and this time we have a resistor and an inductor in our network, and the impedances of both elements are 10 ohm. We start again. We measure the current, and we have an ideal AC current source here, and our current is still 1 ampere. And now we measure the voltage here, and the voltage is 14.14 volts. Okay. And the electric power, the active power is 10 watts. What's that? We have a voltage of 14.14 volts. We have 1 ampere, and the result for the active power is 10 watts. Let's have a look at the voltage at our two elements here. If we measure those voltages, we have a voltage drop of 10 ohm at the resistor. Yeah, it's Ohm's law. The resistor has a resistance of 10 ohm and we have a current of 1 ampere, so the voltage drop will be 10 volt. And at the inductor we have a voltage of also 10 volts. Okay, the impedance is 10 ohm and the current is 1 ampere, so this leads to 10 volts. But why is the sum of these two voltages 14 and something volts? This is because we are in an AC network. Let's have a look at our phasor diagram. Let's start with the current because it's the same in all elements. And then we know that the voltage drop at the resistor is in phase. And we know that the voltage drop at the inductor has a 90 degrees angle to the current and the voltage is leading. That means in our phasor diagram, UL shows into this direction. And the total voltage we measure is the sum of these twos. And if we have a look in our phasor diagram, we measure this voltage. And our voltmeters can only measure the absolute values. They don't know anything about the phase shifts, and therefore we measure at our resistor 10 volts, at our inductor we measure 10 volts, and the total voltage is the absolute value of this complex voltage here, and this is the 14.14 volts. Okay, and we call the power consumption of the resistor active power, and we can calculate it as before. It's the current in square times R. And if we use our number values here, this is 1 ampere square times 10 ohm, so the active power consumption is 10 watts. And this is the value our wattmeter shows us. And now we have the reactive power. The reactive power can be calculated in the same way, but if we have an inductor or a capacitor, then we know that this is reactive power. And if we put in our number values, this also leads to a value of 10, but we don't call this watt reactive power, we call volt ampere reactive. And in the end, there is a so-called apparent power, and this is just the multiplication of the total voltage drop and the total current. So in this case, it would be the 14.14 volts times 1 ampere, so it is 14.14, and the unit for the apparent power is volt ampere. Let's have a look into time domain. So again, we had our current given from our ideal current source. And then we have a voltage drop at our resistor. And this is in phase to the current. And then we have a voltage drop at the inductor, and it has the same absolute value because both elements have the impedance of 10 ohm, but here we have a phase shift and the voltage at the inductor is leading to the current. Okay, in the next picture I will draw the current again, and now I want to draw the total voltage. So now I will add the two voltage curves from the first graph for every single moment, and this leads to this. And now I calculate the power consumption of our load by multiplying the total voltage and the current for every moment, as we did before. And the result looks like this. And you see, the mean value is our 10 watts, so the value of our active power. And you also see that the power consumption of our network is positive the most time, but there are time periods where the power consumption is negative. So if we have a phase shift between current and voltage, and the absolute value of this phase shift is bigger than 0 degrees but smaller than 90 degrees, then we have active and reactive power consumption, and that means that the mean value of the power consumption is positive, but there are time periods where the power consumption is negative. So let's have a look at our last example. We found out that we have active power consumption of 10 watts, a reactive power consumption of 10 volt ampere reactive, and that the apparent power is 14.14 volt ampere. And we had this phasor diagram for the current and the voltages. And now we can draw nearly the same phasor diagram for our power. And our active power is considered to be a real part. And the reactive power is the imaginary part, and the sum of the two is the complex apparent power. And you see, it works here too. We had 10 watts here, and we had 10 volt ampere reactive, and that leads to an apparent power of 14.14 volt ampere. So we can calculate our apparent power with Pythagoras. And we could also express our apparent power as a complex number, and then the real part is the active power and the imaginary part is the reactive power. And that also means that the active power is the real part of the apparent power, and the reactive power is its imaginary part. Let's have a look at another example. Here we have the series connection of an inductor and a capacitor. And we already know that these elements only consume reactive power. So we don't have to pay anything if we connect this here to our power network. Okay, I will draw our voltages and currents again. Our current is the same as before. The RMS value is 1 ampere. And this leads to a voltage drop at the inductor. We have a phase shift of 90 degrees. The voltage is leading. And at our capacitor, we also have a 90 degrees phase shift, but this time the current is leading. And when both of our elements have the same impedance, then this means when we have our current, I changed the scale of the y-axis, therefore the current looks bigger here, but it's again only an amplitude square root of 2 times 1 ampere. And if we add now our two voltages, this leads to a total voltage of 0 for these two elements with the same impedance. And that means that the power consumption of our circuit here is 0 all the time. And this is because the two voltages cancel each other out. And if we think about our reactive power, we could calculate it because in every element we have our current flow. Therefore, we could calculate a reactive power for our inductor and a reactive power for our capacitor. But the sum should be 0, and therefore we count the capacitive reactive power with a negative sign. Okay, so how could we calculate the power in an AC network if we know the complex voltage and the complex current? Let's have a look at our resistor. There we know that we only have active power, and active power should be a pure real value. So we have no imaginary part in our power there. So let's have a look. Let's say our current has this phase shift here. And therefore we know that at our resistor, voltage and current are in phase, so the voltage will have the same direction. And now we used to calculate the power as a product of the voltage and the current. And both of them are here complex numbers, and if we multiply them, we multiply the absolute values and we add the phase angles. And here this would lead to a phase angle of nearly 90 degrees, but our active power should have the phase angle of 0 degrees. And therefore we use a trick for the definition. We have a look at the conjugate complex current. Conjugate complex was the number with the same real part and with the imaginary part with a flipped algebraic sign. And now if we multiply the voltage and the conjugate complex of the current, this leads to an apparent power which is pure real. And this leads us to the definition of the apparent power. It's the product of the complex voltage and the conjugate complex of the current. Let's have a look at the inductor. At the inductor, let's say we have the same current again. And here we know that the voltage drop is leading by 90 degrees. So it will have this direction. And if we now calculate the apparent power, then we take the conjugate complex of the current. And if we now multiply the voltage and the conjugate complex of the current, this leads to a pure imaginary number. And this number is positive, and therefore it's what we need. We said that at an inductor, the reactive power is positive. Okay, let's have a look at the capacitor. Again, we have the same current here, and this time the voltage is lagging. And now we do the same thing. We want to calculate the apparent power, and therefore we need a conjugate complex of the current. And if we multiply voltage and the conjugate complex current, then it leads to an apparent power which is pure imaginary and with a negative sign. Hey, cool! We wanted the apparent power at the capacitor to be negative, and now this happens automatically. And in the end, let's have a look on a series connection, this time of a resistor and a capacitor. If we start with our current, we know that the voltage drop at the resistor is in phase, and the voltage drop at the capacitor is lagging. And that means if we want to calculate the total voltage, it is the sum of the single voltages, and this will look like this. And now we need our conjugate complex current, and if we multiply our total voltage and this conjugate complex current, the result is here. So you see, the apparent power now is a complex number, and the real part is the active power, and the imaginary part is the reactive power. And here you see the reactive power is negative, and yeah, that's logical because we have a capacitor in our network there. And now I want to show you different phasor diagrams to show you an important thing there. Let's say this time we have R and L in series. And there is again a current. And I draw a current for the phasor diagram. And we've already seen the total voltage drop here will look something like this. The voltage will lead, and because we have an ohmic inductive element here, the phase angle here would be bigger than 0 degrees. 0 degrees would be the resistor alone, and it would be smaller than 90 degrees because then we would have only an ideal inductor. So it will look like this. And now we could also draw a phasor diagram of the impedances. The impedance of the resistor is just the resistor value, so it's a real number. And the impedance of the inductor is j omega L, so it's a pure imaginary number. And the total impedance is the sum of them, and it looks like this. And the cool thing now is that we have in this phasor diagram the same phase angle as we had in our phasor diagram with current and voltage. And now let's have a look at the powers. We have active power, which is pure real. We have reactive power, which is positive imaginary here. And we have our apparent power, which is the sum of the two. And the very cool thing is that here in this phasor diagram, we also have the same phase angle. And this is super helpful. Sometimes you only know, for example, the apparent power and the active power of a device. And then you can calculate the phase angle with that, and the phase angle can be used for the other phasor diagrams too. And we will see it in our exercise task that this is very, very useful. And don't forget, you have your same phase angle in all these three phasor diagrams. In the end, I want to say something about reactive power compensation. Why should we compensate reactive power? I said we don't have to pay for that. Yes, that's true, but reactive power means that we have currents on our power net. And these currents will produce voltage drops because the cables of our power net are not ideal. They have ohmic losses. And reactive power leads to higher currents, and these higher currents leads to losses. Okay, and now let's say we have a load which is ohmic inductive. And yeah, let's draw a phasor diagram. I start here with our current, and we know that the voltage drop at the resistor is in phase. The voltage drop at the inductor has a 90 degrees phase angle, and the voltage is leading. So you see the total voltage will be this here. And now you see we have a phase shift between the current and the total voltage, and therefore we will have also reactive power in our system. And how can we compensate this? We want that the voltage and the current at our source are in phase. Okay, and what we can do is we can add a capacitor here. As I said, a capacitor does not consume active power, therefore it's for free to us to add a capacitor to our network. And let's have a look what happens. There will be a current flow through this capacitor, and this current will lead by 90 degrees to the voltage. So to the total voltage of the source, because this capacitor is connected in parallel to our ideal voltage source. Okay, and if we want to calculate the total current here, that will be the sum of the two subcurrents here. So if we draw it like this, this will be the total current. So with the capacitor value I used here, we don't have perfect reactive power compensation because the phase shift between current and voltage is smaller now, but it's still there. But if I use the best value or the correct value for our power compensation, then the current through our capacitor will be bigger, and this will lead to this situation. So you see, we have an additional current through the capacitor, and this additional current leads to a smaller current from our voltage source, and our voltage source only delivers active power to the network because the total voltage and the total current are in phase.